Okay, page 12. I think we did 16, right? All right, let me start off with 17 then. So we're still we saw an example of cross-section volume. We saw an example of washer method here. Let's look at 17 here. Okay, what's the volume of the solid generated when the region bounded by the graph of x equals root y minus 2 and the lines x equals 0 and y equals 5 is revolved about the y-axis? Now, it may be kind of hard to know exactly what that graph looks like because it's not in the form that we're used to. Let me just rewrite it to solve for y so that it's easier for us to visualize what's happening. So if I square both sides, I get x squared equals y minus 2. And from here, if I solve for y is equal to x squared plus 2. So this is basically a parabola opening up with a y-intercept of 2. So this is what our graph looks like. Okay, technically, the parabola extends to the second quadrant, but we have boundaries at the line x equals 0 and y equals 5. So it's just going to be this kind of a quarter circle region looking shaded first quadrant. Okay, we're taking that shaded region, we're rotating about the y-axis. So anytime we see rotation, we know it's either this method or washer method. And then based off of where our dotted line is and where our shaded region is, what can we say? Disk or washer method? Disks, right? There's no gap between the shaded region and the dotted line. Not like this one, right? Where basically, even if this was touching, if it's up against a curved region, if there's any sort of a gap, we got to go through washer method. We got to subtract out some sort of a hole from that with that little r. But here we said this method, and all we need is one radius. So from the dotted line, we can extend to our boundary. And we see a horizontal radius. So what equation, how do our equations have to look? In terms of what? Yeah, x equals, right? X equals. Now the equation is already given to us in that form, so that's fine. We can just use that then. I did rewrite it because I wanted to visualize the graph a little bit easier. But we can just use what they gave us there because that is in the proper form. Okay, our axis is x equals 0. We just have to build our big radius. So right minus left. What's the right endpoint of big radius sitting on? Sitting on the square root, right? Minus, okay, what's the left endpoint of radius sitting on? 0, okay. So all we need for volume is just pi integral of big radius squared. We can drop the 0. The 0 can just go away. And what are our bounds going to be? Our bounds have to be in terms of what? Y, yep. So what's the lowest and highest y value that you see within the shaded region? 2 to 5, yeah. So sometimes you can just look at the graph and tell. If it's not as easy to tell, then you may have to graph it and actually look for an intersection. But in this case, we can tell. Okay, all right, see if you guys can finish off this problem. And then you can plug in the calculator after that. Looks like the answer choices has the decimal value with the pi included in the decimal calculation. So you got to enter in pi into your calculator as well and get that decimal value. Okay. Any questions here? All right, let's go to page 19. Okay, page 19. Yes. All right, here's page 19. So again, at the top, you're going to see these are the topics that we are focused on for Tuesday's test. And let's look at number one here. So number one, it says find the derivative of a definite integral. What does this remind you of? What theorem is this? Second theorem, right? So second fundamental theorem of calculus. Let me remind us. Okay, so the theorem says if I find the derivative of a definite integral, my upper bound being the variable, my lower bound being the constant, then all I do is I can wipe these two operations out, but this upper bound variable will have an impact on my function. I'll enter that upper bound into the variable of the expression, but I need to multiply the expression by the upper bound's derivative. So f of p of x times p prime. So we're going to apply that for this problem here. So what's going to happen if I follow, because I know that these two operations will cancel each other out. This e to the 4x squared is not going to change much. So how will it get impacted by the upper bound? Becomes what? E to the 4z squared times 1. Yeah, z's derivative is just 1. So times 1, right? There's no plus c here. Because ultimately that derivative is going to wipe out any constant that's going to come out of it. So just d. All right, number 2, the definite integral from 0 to 2 of 2x cubed minus kx squared plus 2k dx equals 12, then k must be. We know k is a constant, so pretend like k is just like a 3 or 5 or 6. We don't know what that number is, but let's go ahead and find the antiderivative like we normally would, right? We go through power rule, plug in upper and lower bound, and then we set equal to 12, and we can solve for k. So let's ignore that equals 12 for now. Let's just focus on the indefinite integral. So every term we can apply power rule, right? So 2x cubed becomes what? Wait, power rule for antiderivatives. Yeah, 4th over 4. Okay, I'll reduce that later. Minus, what does kx squared turn into? All right, what does 2k turn into? Good, 2kx, not 2k squared over 2. Remember, 2k is just some number in front. So if I have a constant, the constant will turn into a degree 1, so it becomes 2 k x. Okay, again, we're going to ignore that 12 for now. We're just going to go as far as we can go with our depth integral. So I can plug in 0 and 2. Which number do I plug in first? 2. Okay, I'm going to reduce this here. This is really 1/2. So 1/2 2 to the 4th minus, what does this become? Times, which is 8, right? So minus 8/3 k plus what? Okay. All right, minus my upper bound minus, now what's the nice thing about the 0 here? That's going to wipe everything out, right? 0 minus 0 plus 0. So that's nice. We don't have to worry about that as much. So I have this being 8. Right, 16 over 2 is 8. So 8 minus 8/3 k plus, sorry, not 4x, it would be 4k. Now we can do what? Set this equal to 12. Yeah. Right. Now we can solve for k because that's the only variable left, right? So now we just have to do some simple algebra here, combine like terms, do common denominator, and then get k by itself. Okay, so combine like terms here. I know I got to do common denominator, so I made that 4k into 12 over 3 to match common denominator. 12 minus 8 is 4. 4/3 k equals 4. Dividing by 4/3, same thing as multiplying by the reciprocal. 4 and 4 cancels out. K equals 3. All right, number 3. Integral of x over x squared minus 4 dx. Too many terms in the denominator. We can't split up. We can't just use power rule. What does this look like to you? We got to go through what? Use substitution. Okay, what's our u value? What's our u value here? Yeah, the entire denominator. Okay, so try that. See if you can work your way through and figure out what the coefficient is. See if that x in the numerator cancels out, and then decide what rule you're going to use once you get everything in terms of u. There's leftover 1/2. What's the integral of 1 over u turn into? Here we can use what rule? Natural log, right? What if that u was different power? What if it was u to the 1/2 or u squared or u cubed? I got to do what? Bring it up and do power rule, right? Yeah, so the only time you can do natural log is if it's u to the first power. I know sometimes we get caught wanting to do natural log every time, but pay attention to the exponent. If it's not exponent 1, we got to bring it up and do power rule. Okay, replace the u back in terms of x, and we have our answer. Oh, I want to point something out here. Sometimes AP exam can go a little further than this. Any idea what else can be shown besides this form? How can an expression be reduced or be condensed past this point? Basically, what's another way to write this? It has to do with this 1/2. Where can this 1/2 be placed? Okay, yeah, in the denominator, but also a log property. What's a log property that we can use? Exponent. So this can be brought up as an exponent, meaning it's natural log of x squared minus 4 to the 1/2. And how else can this 1/2 be written? As square root. Yeah. So just wanted to. No, you don't. But I do want to point out that if this is what you have, but the answer choice is this, you need to be able to know how to get from here to here. Does that make sense? It is. It is. But I've seen it on the multiple choice section where this is the answer that you get, but then this is the way that the answer choice is given to you. And then we have to make that connection that this 1/2 can be brought up and that it can be rewritten in a different form. Right. Power property for logs, yes. You're right. The absolute value would have to be in place unless they specify that x is greater than 2. Yeah, but you're right. That unless yeah, that absolute value will have to still be there to ensure that we're not getting a negative number. Okay, page 20. Let's do number 5. It says the function is continuous on a closed interval from 1 to 5, and values of the function are shown. If the values in the table are used to calculate a trapezoidal sum, the approximate value is equal to. So you guys just recently took your FRQ, and there were some versions that had trapezoidal sum on it, and I think there were some issues with us remembering what the area formula for trapezoid is, or remembering incorrectly, and then just kind of threw off a lot of the answers. Do you guys remember what is the area for trapezoid? Yeah, H1 plus H2. Okay, so some students will forget about that 1/2, or this is what would happen. I know this is not our problem here, but let's say there was an interval here. Students would say 3 minus 1, which is 2. That's fine. But then they would pick the middle number and they would just put 3 instead of 4 plus 7. Or they would add 1 plus 3 instead of 4 plus 7. So remember, the width is coming from the first row. The height is coming from the second row. And you're only adding the heights where your bracket is falling on. So make sure that you don't include that 3. I know that we may want to use that 3 because we're thinking middle rectangles. Middle rectangles, you just use that number. But this trapezoid, you're only using the heights at the ends. Okay. Or I see students, yeah, they would do 1 plus 3, or they would forget about the divided by 2, or they would use the middle y value. Okay, so I know that's not this problem here. This problem, it says use the values in the table. So that means we want to use as many intervals as we can. So we want to go from here to here. Now, what's the width of each of these subintervals? Just 1, right? So the width will be 1 for each of them. Okay, so if you guys can see if you guys can set this up. Can you set up each of the 4 areas for each of your trapezoids and line them up, and then we can add them all with our calculator. Okay, what do we get? Yeah, 14.5. All right, number 6. Uppercase F is the antiderivative of lowercase f. So we know that uppercase f is the integral of f, which is telling us that lowercase f is the derivative of f, of uppercase f. Right, so we see that derivative relationship here. This is basically at the uppercase f prime level. So we have a f prime, uppercase f prime. We have a location, a starting point on the upper case f function, and then we are looking for a certain value. So I like to think in terms of particle motion, where final equals initial plus displacement, right? So we can final position equals initial position plus displacement. So I can say f of b is equal to f of a plus the integral from a to b of f prime. See if you can use that formula to adapt for our problem here, and the rest can just get plugged in the calculator. Okay, any questions with 6? Okay, page 21, number 7. All right, f uppercase f and lowercase f are continuous functions. Uppercase f prime equals f of x. So we know lowercase f is the derivative of uppercase f. We want to find the antiderivative from 1 to 3 of a lowercase f of 3x. So we got to go through our antiderivative rule. We know lowercase f, which is turned into uppercase f. But that 3x, we got to do a little bit of what as we go through our integral process. Yeah, u substitution, right? That 3x is going to produce something along the way. So we'll go through our u substitution steps, but everything is in terms of in function notation. Right, let's convert everything in terms of u. So f of u times du over 3. This really pulls out a what in front? Third. Okay, I'm not going to worry about the balance just yet. Lowercase f becomes what? Antiderivative. Uppercase, right? So the 1/3 will come along with it. So uppercase f of u. I do want to involve the bounds, but I should bring back what? 3x. Okay, so once I bring back 3x, then I can work in my bounds from 2 to 5. Or if you want to leave it in terms of u, you can just have to push the 2 and 5 through the formula to get it to be in terms of u. So just make sure that you don't do a mismatch, right? The 5 and the u are mismatched. You got to either use the 3x and 5, or you use, if you from u, you want to use 15 and 4. But right. So now we can plug in upper and lower bounds. 5 times 3 is 15 minus lower bound f of 6. Okay, the average value on the interval from 0 to 4 is, so what formula do you think we have to use here? Average value theorem, right? So that 1 over b minus a formula. Okay. Replace all your a's and b's with what? 0 and 4, yep. And then this is what we have, 1/4 integral of e to the 3x. But once we're here, we still have to go through what in our integral process. Yeah, u substitution, u being the 3x. We go through u substitution, get everything in terms of u, keep track of our coefficients, and then e to the u becomes e to the u. Bring back your original variable, and then you plug in your upper and lower bound. A few minutes left. I just want to talk about number 10 real quick on page 22. It says the integral from 0 to 1, square root of x, and then x squared plus 3x minus 8. I want us to be able to work this out by hand. How would you go about going through this problem? We need to use substitution here. We can just do what? Yeah, distribute everything through, and then every term can use what for integral? Power rule. Yeah, so this is just an expansion power rule problem. Once you get all your terms all cleaned up, you go through power rule, and then you plug in your upper and lower bound, and you get down to your answer.
We can distribute it.
Sorry?
We can distribute it.
Exactly, yeah, if you distribute, there's just one term. Exactly. And also, there's no messy exponent, like it's not raised to the fourth where it's hard to get into that. Okay, so I think we got through a good, most of 4 problems from 19 to 22. The remaining problems, I want you guys to finish for homework. I'll send out reminders Sunday, I'll check it Monday, and then we can move into our FRQ packet 5. Okay, and your test is on Tuesday. Help session Monday morning, this afternoon, Monday morning, Tuesday morning, and then your packet for pages 9 to 12 and 19. Will be your we'll be checking on Monday. All right, come get your phone.
Get the phone. Oh, for I watch the sun go down and makes me right back up. Sure. You need to get through the.
I'm sorry?
Do separate intervals, or do you have to?
You have to, because it's multiplied. We can't do square root of x times. Yeah. We can't do that yet.
Dude, I had a conversation with mom when I was like, hey,